Okay, so this is the second part of the lecture on principles of nutrient management planning, and this part is about nitrogen fertilizer rates and how we come up with optimum nitrogen fertilizer recommendations in the UK. And like everything to do with nitrogen, I suppose it's a bit more complicated than phosphorus or potassium, so a little more involved, and that's of course because of what we know about the nitrogen cycle, it being this dynamic, volatile element that changes form all the time due to, soil type and microbial activity and environmental conditions and all those things. So it makes it challenging, but of course interesting also to try and manage. Here's just a image taken quite a while ago, actually, in one of our long-term experiments at Nafferton Farm. I'm sure you've all seen this sort of evidence before of if you do put nitrogen fertilizer on. So in the forefront of that picture, you can see the plus N fertilizer plot winter wheat that have had, I think it's winter, it might have been spring wheat actually that year, that had nitrogen fertilizer applied, and then the area sort of to the back, minus N fertilizer, no N fertilizer applied. Just to remind us all, I'm sure we know already, crops really like to get lots of nitrogen. Of course, it doesn't have to come from fertilizer. We can supply it from other means, manures and legume plow downs and that kind of thing. But there's no question that, especially the modern varieties of crops that we grow, are really designed to respond, as we say, that's that term, plant response, to increasing levels of nitrogen to grow better and give us more yield. So today we're going to really understand why estimating on fertilizer requirements is so difficult. We're going to talk about excess winter rainfall. So even though we're talking about nitrogen fertilizer, we're going to get into some soil water a little bit and rainfall. Why is it important for nitrogen management? There's two different ways to estimate what we call the soil nitrogen supply. So we'll go through that, and then we'll look at, again, our favorite subject, calculating fertilizer application rates. So those are the main things we're trying to achieve today. And like I said before the other lecture as well, we're going to have a practical class on Friday where we'll go through a lot of calculations and kind of reinforce some of these concepts that I'm talking about in these little recorded lectures. So here's that crop nutrient response curve again, just like I showed you in the last one, but just to reiterate some of it. I think this one I've got some points, some additional points on it. So yeah, along the x-axis we have this nutrient supply shown, and again we have the nutrients coming from the soil. So with the phosphorus and potassium, we do soil tests, and we can get a fairly good idea of the relative ability of different soils to supply phosphorus and potassium based on a soil test that we might do in the field once every couple of years. For nitrogen, it's much trickier. So that nitrogen from the soil, or the soil nitrogen supply, very difficult to estimate that. We don't have a reliable soil test in the UK for that, and so we have other ways of trying to do that. But that's one of the challenges with managing it. But we're, of course, trying to get that on-farm economic rate, as I talked about that again in the last little lecture about break-even ratios and how that's related to cost of the fertilizer versus value of the crop. And so in order to get that up to that, to get that optimum yield, then we have to supply N additional to what's provided by the soil. We've got to apply it coming from fertilizer or organic manures. And that's really the name of the game, what we're trying to do when we're trying to come up with optimum fertilizer nitrogen recommendations. So they're difficult, as I said, because estimating soil nitrogen supply is very difficult. So like I said, nitrogen is very dynamic. It changes form all the time depending on the weather and on what we've been growing in the crop the year before, what we've put on the land, all that sort of thing. It's very susceptible to losses. So like I've mentioned, I think, in our lectures this year, we're having such a wet year this year that no doubt we're losing a lot of nitrogen this year due to leaching or denitrification. And then, of course, soil organic matter. A lot of nitrogen gets released by this process we've touched on called mineralization, right? Well, how do we predict that? How do we know how much nitrogen is going to be mineralized from the organic pool in the soil in a given year? Very difficult to predict that. Nonetheless, we do try. So we try and estimate soil nitrogen supply. And it's basically, soil nitrogen supply is the amount of nitrogen in the soil, apart from that applied for the crop in fertilizers and manures, that is available for uptake by the crop throughout its whole life. And it's affected by things like residual N, so how much nitrogen was left over after we harvested the last crop, how much N has been leaching, so just like I mentioned, leaching of N over winter has probably started already or a month or more ago this year because of our heavy rainfall, and that's linked to excess winter rainfall in soil type. And then it's also affected by how much nitrogen is mineralized from soil organic matter. So excess winter rainfall, really important. It's the actual rainfall between the time when the soil profile becomes fully wetted in the autumn and then what we call the end of the drainage period in the spring.
Before Friday.
And have a go at calculating the total amount of nitrogen applied in 30 cubic meters per hectare peak slurry. So you get that value
on
actually out of a
table
in a few weeks' time.
So we'll
how much is available, that's where you have to then look at what percentage of total
just what it says.
and
in
the
peak
autumn
slurry is
we
available
have the soil
based
that
on
might be
those
dry
application
summer,
conditions like
warm weather and a lot
time
of
of year it was
transpiration.
applied, that it was
And then gradually in
incorporated.
the autumn, the weather gets cooler, we
and,
harvest the crops, they stop
that sort of
transpiring
thing
so
as
much,
well.
and the
And
soil
then,
profile basically
then
wets,
figure out how
gets
much
wetted
additional
up.
nitrogen you
Eventually,
might need to apply.
the whole
So that's a
soil
good little
profile
exercise
is
in doing
wet,
some calculations.
almost
You can have a go at that. And
when that
again, I think I'll go
happens,
through that
any
on
rainfall
Friday
that
as
falls
well
on
in the
the top
practicals. So we'll run through some of these
comes out the
calculations on the
bottom,
practical before
displaces
you
some
get
water
working
in it,
on your
comes
own
out the bottom. So it's a
calculations
bit like
in that
yeah,
class.
it's
And
a
the
bit like
practical
a,
class
what do you think
on
of it?
Friday, don't forget, this
I'll try
is
and
actually an
draw the
assessed
picture
one
here,
where
just
you're going to
simply
write a
this is what I would
report
have
and
drawn on the
hand
board
it in.
if we were if I was seeing you.
So
Basically,
soil chemistry
you
one,
have
where that
water
one,
moving
soil
down
chemistry one
and
is,
then out of the bottom
for a
of the soil profile.
blackboard online
So any
assessment.
rain
This
that comes
is
in
actually
the
a written
top,
report that I'm going to have you do on the
once the
nutrient
profile is
management
fully
practical
wetted,
Friday,
it
so
comes
make
out,
sure
falls out the
you're there
bottom.
for
So
that.
at some
And
point
that's it till
in the autumn you
Friday,
get to a
that
point
should
where
say
the
Friday,
profile
not
is fully
Thursday,
wetted,
but,
and then any more
anyway,
rain that
hopefully
comes
the
in the top
calculations aren't
goes out the bottom.
aren't going to be
That's what we
too
call
much
excess
for you. I
winter
usually
rainfall.
find
So
that
we just basically
pretty
count
good at this
millimeters of
actually,
rainfall
because
from
most of
that
you are
date in the autumn
from farming
when
backgrounds
we
and you're
decided
used
the soil
to
profile is
doing
fully
these sorts of
wetted.
calculations,
Like I
for
said,
seed
this
rates,
year probably
pesticide
is fully
applications,
wet.
that kind of thing. So
Hopefully
we'll be
September
able to figure it
or even
out.
early September because
Okay,
it's so
see you
wet.
on Friday.
And after that, every additional millimeter of rain that fell, we could count as coming out the bottom. So this affects nitrate losses by leaching during winter, because we know with that rainfall, of course, nitrates going out the bottom of the profile, and we're losing it. So if we have high excess winter rainfall, high losses of N by winter leaching, and that means next year there'll be less nitrogen in this soil rooting zone for the crops growing next year. So that's why it's important. So soil type plays a role too. Some soil types you're going to have higher rates of N leaching than others. I guess you can guess which ones, right? Tend to be our sandier, lighter soils that don't hold so much water in the profile. They'll fill up faster and then start draining out the bottom. So how do we assess soil nitrogen supply? So what we're trying to get to is this this concept called the Soil Nitrogen Supply Index, so SNSI. And there's really two ways to do it. One of them is this measurement method, and that's appropriate where we think the soil nitrogen supply is going to be quite large and uncertain. So this is fields that have a history of organic manure application, vegetable rotations, where the timing of residue incorporation might affect soil mineral N, and also where nitrogen residues might be large following outdoor pigs. Just to remind you, soil mineral N, what do I mean by that? SMN, so that is the nitrate and the ammonium. Actually, I wonder if I can erase that. No, I can't. I meant that to be plus. Yeah, this is actually a minus, of course, and that's plus. So it's a nitrate and ammonium in the soil profile is the soil mineral N, and we remember that's the stuff that plants take up, right? So we're trying to estimate how much nitrogen will be supplied to the following crop, and part of that is actually measuring soil mineral N, but there's more to it than that. I've written over that bit, but on a given date, soil nitrogen supply includes these three components then. The soil mineral N, so I've actually got it there in type, nitrate N and ammonium N in the rooting depth. Any nitrogen already taken up by the crop, and then any what's called mineralizable soil N. So that's nitrogen that will be mineralized from the organic pool. So when we measure, do soil nitrogen supply by measurement, first of all, we take a measurement of soil mineral N. I put a picture here of one of my students a few years ago using our deep soil sampler at Nafferton in some potatoes. Now, this is not when you would actually measure soil mineral N for SNS. You normally do that measurement in the in winter, sort of mid to late winter. But I'm just showing it because it's to remind us that it's quite a deep soil sample you need to take, down to sometimes 90 centimeters, so to reflect the rooting depth of the crop. And that's a machine we have at Nafferton that does that type of soil sampling. But so you do a soil mineral N sample in the winter, so late February, March time. Then you also estimate how much nitrogen is already in the crop if you've got a winter sown crop. So you use this green area index method to figure out just how much nitrogen did the crop already take up. And there's guides. Nowadays you've got little apps on your phones where you can take photographs of your wheat or barley and then get it converted to green area index, or get it converted right into kilograms N per hectare. Just an approximation of how much nitrogen the crop's taken up. And then this is just also showing again a table that shows how you might estimate the nitrogen taken up by the crop at a given time. So this is just approximate, but showing you could count shoots per square meter. So if you don't use the app on your phone to take a picture, nowadays that's a little more of the modern way to do it. Prior to that, we used to use tables like this where we'd count shoots per square meter and then kind of get a bit of an estimate of what the nitrogen content was in that crop. And there you can see some of the pictures that are in RB209 showing you green area indexes, and then a little table 4.7 for oilseed rape, where you can convert a green area index ultimately to crop N. So it's all just to try and get an idea how much nitrogen is in the crop already. So we do that soil test I showed you previously for how much mineral N is in the soil. We look at the crop that's there at the time of our sampling to figure out how much nitrogen is in the crop. And then the third thing we do is look at what's called soil mineralizable N. And this is the big unknown, really, because we're trying to estimate how much nitrogen will be mineralized over the season. Can't do that at home. We need to send our soil off for a soil test, and what we usually do is an incubation. So we'll take a sample of soil and we'll incubate it for about a week, and then we'll look at how mineral N changes. And we actually do an anaerobic incubation. So in that we'll have organic, basically that's organic N, and it's getting converted to what? Ammonium. Because it's anaerobic, now normally when we study the N cycle, remember that ammonium N tends to go on to nitrate, but because it's anaerobic, that doesn't happen. So we just get ammonium accumulating. So we incubate for about 7 days, and then you measure your ammonium levels at the beginning of the 7 days and the end of the 7 days, and that gives you an idea of how much mineralization potential that particular sample had. So the laboratories have sort of done hundreds or thousands of these samples over the years, and they have a pretty good idea how to interpret the results of a 7-day incubation and convert it into what will be mineralized over a typical growing season. So with those 3 steps, you come up with a number of what is the soil nitrogen supply from a given soil. And here you can see you sum up, so you add up your soil mineral N to 90 centimeters. That was that machine I showed you. The nitrogen in the canopy, that was that growth area index, and then the mineralizable N, the incubation. Sum them up, and then you look at this table in RB209, and depending on what the number is, you then read over and get your index from over here, you see. So just like, at this point it becomes just like phosphorus and potassium. You then work from an index to come up with a fertilizer recommendation. Now that's what we call the measurement method to come up with soil nitrogen supply. Quite involved, I think, as you can see. Requires going out and sampling, doing some calculations, sending your soils off for some laboratory analysis and that sort of thing. The other way, and the more common way that people do come up with soil nitrogen supply, is this field assessment method. And you can find that in the new version of RB209. Every recommendation chapter has this described at the beginning of it, and we'll do it in the practical class on Friday as well. So in this case, you just sort of go through these steps of, for a given field, you identify the soil type, the previous crop, you decide whether you're in an area that has low, moderate, or high excess winter rainfall. So you do that by looking at a map of England and then just identifying where you're located on that map. And then you identify your provisional soil nitrogen supply index using one of the tables, A, B, or C, depending on rainfall, or D if it's just been in grass. And then you may make a few adjustments based on some notes in RB209. But basically, you just look it up in the book, basically. It's the book method. And most people use that unless they've got a situation where they're very uncertain about the nitrogen supply from a field because, like I said at the beginning, if it's had a history of manure applications or recently had outdoor pigs on it, some reason, or some vegetable crops where you're not really sure how much residue was left behind, then you may want to try using the measurement method. Otherwise, you'd use this field assessment method. So here's an example. We would need the RB209 in front of us to follow this through, actually, which I don't think I've got it. Yeah, I don't have it here. We'll probably maybe have a look at this in our practical class on Friday as an example. But basically, you could do this yourself too. You could have a look at RB209, the sections on soil nitrogen supply, and just follow your way through, looking at what the previous crop was, where you're located, what soil type you're on, where you're located in the country, and then what the soil nitrogen supply index is in that area. So that's an example. I guess this is for winter wheat following vine peas. Yeah, we'll do that in our practical class on Friday. Here's an example of sort of what your tables look like. So a little bit more complex than the phosphorus and potassium ones because they also have this soil type section on the left, you see. So you have to actually choose the row that's applicable to the soil type in your field. And then you just read across, and depending on the index, find the appropriate nitrogen rate. That's not all of it, though, of course, because you then have to consider how you're going to apply that nitrogen. So you don't normally, if it's anything above about 150, you don't normally put it on in one application. You usually split it. And that's sort of explained here. Oh yeah, 120 it says. So if less than 120, you might put it all on as a single dressing. This is for wheat. If it's more than that, then you might put 40 on at first and then maybe the rest on in one or two further applications. So there's quite a lot of detail in RB209 on sort of the timing of these applications, and that's all related to trying to make sure that it goes on when the crop really needs it, and there's not surplus N sitting around in the root zone when the crop isn't able to take it up, because then it's susceptible to loss. Here are some of our fertilizer sources. So ammonium nitrate, popular one, 34.5. Anhydrous ammonia, this is obviously for North America. I don't think we use anhydrous ammonia here in the UK. Probably a good thing. It's quite a bit of a scary chemical that you get injected into the soil. It's from a big tank of ammonia gas that gets injected into the soil. Ammonium sulfate we use here, and urea, of course, as well. And you can see, like P and K, they're not 100% N, any of these sources. So when you come to the calculation stage, you're going to, of course, have to keep in mind that these percents mean that for every 100 kilogram of that material, that's the number of kilograms in 100 kilograms. Yeah, so this is the calculation we would have to do, but we're going to skip that and do that in the practical, I think. Or you, as I said, you could have a quick go at it beforehand if you want to have a look at RB209 and see if you can figure out the SNSI and then the how much N would be needed and do the conversion. And compound fertilizers. Oh yeah, so just when we thought we had everything figured out, compound fertilizers a little bit more complicated still, because they're blended fertilizers where you're applying the 3 nutrients at once, or 2 or 3 of them at once. So here you can see some examples And the NPK column on the left is just showing you the ratio. That's useful. So if you know the approximate ratio of nutrient needs in your field, so let's say you've got a field that needs, just going to make this up, but let's say it needs 150 kg of N and 75 of P and K, then you know that 150 to 75 to 75, you could see that you could then choose this one, because that's their same ratio, isn't it? 2 to 1 to 1. So that's why the ratios are useful. If you try and approximate, choose a blended fertilizer that has a ratio of nutrients similar to the ratio that you need to put in your land. But of course that's going to be difficult, because one field may be different from another, and you're not going to maybe want to buy a whole bunch of different types of blended fertilizers. So that's lots of fun and games when we do the calculations with those, which we'll work on Friday, so you can figure out how to meet the fertility needs of one of the nutrients and not apply surplus of another. What about nitrogen in organic manures? Now that is even more complicated. Many nutrients are in the organic form, but how do we know when they're going to be available in plant available form? Very tricky. Again, it's about predicting that mineralization. That's really difficult. And it's also difficult to balance the supply, right? Because the NPK ratio in your organic manures can't be easily modified. So you're sort of stuck with the way they are with that ratio. So you might find that the ratio of NPK is not at all balanced with what your crop needs. And you have this risk of oversupplying one nutrient if you balance for another. So let's say you decide, I'm going to apply, make sure I meet my 100 kilograms of phosphorus per hectare from this particular manure source, and you do that, but you may inadvertently find that you've applied 3 times as much potassium as you need, for instance. So it's very difficult, because they don't supply a single nutrient, they're supplying all 3. We'll do some calculations in our practical again on that, so you have a better understanding of the challenges with that. So how do you account for N in organic waste? So there's kind of some different scenarios. So if you've done regular applications of manure to previous crops in the rotation, then your soil nitrogen supply should really be accounting for the nitrogen in the organic waste, because it will have built up nitrogen supply, the soil organic and pool in the soil, and that's going to elevate your soil nitrogen supply index. So if you've been putting regular applications on sort of in previous crops, then your soil nitrogen supply index should reflect that, either by doing the measurements or by adjusting it by 1 or 2 levels. So that's one way you account for it. But then you have the other situation of, if you're just putting manure on recently, so since the last crop harvest, then you do need to treat it more like a nitrogen source and try and calculate how much mineral nitrogen did that particular application of manure provide to the crop, and then deduct it from the crop's nitrogen requirement. And that takes again, some calculations to do that. But RB 209 has a whole chapter on organic manures where that is explained. And again, we'll go through it in the practical on Friday, how we do those calculations. So if we're trying to estimate nitrogen supply from recently applied organic waste, so the second scenario there, we have to keep in mind that they supply nitrogen in 2 forms. So there's the readily available nitrogen. So most manure will have nitrogen in it as ammonium N primarily, not much nitrate N, maybe a bit, but not much. If it's manure from a bird, so from poultry, there'll be uric acid N as well in there. So those are all readily available, very soluble nitrogen forms, almost equivalent to bagged nitrogen fertilizer. Then the other form, of course, is the organic N, so that's the organic matter again that's going to have to be decomposed, mineralized by soil organisms to be released to the plant in a crop available form. It's just showing you some of the different proportions of those. So you can see pig slurry doesn't have any uric acid, got a heck of a lot of ammonium N. So those are showing proportions there, right? So the total is 100, but the pig slurry, you can see, looks like it's about, what is that? At least, yeah, 2/3 probably ammonium N, about 66% ammonium N, and then the rest would be organic N. And the contrast, that was something like old cattle farmyard manure here down the bottom, and you can see it's almost all organic N, and it's got a bit, maybe about 15% ammonium N, but mostly it's organic N. So depending on the source of manure, some of it's got much more nitrogen in that kind of volatile available form. Here's layer manure. About half of it is uric acid or ammonium, so about half of it's fairly available, half is organic. So it depends really on the manure type, and there's lots of information again in RB209 on this. So how do we estimate how much of the nitrogen in those manures is going to be available to the crop? Difficult, isn't it? We have to consider available nitrogen after losses from what? Probably from volatilization, maybe some leaching as well, possibly, primarily volatilization. And then we have to consider the nitrogen released from the organic N during the growing period by what? This is probably a fill-in. This is a fill-in, the blank one from last year. So that's by mineralization, right? So just like when we did the soil nitrogen cycle, you'll remember that organic nitrogen mineralizes into mineral forms like ammonium and nitrate. How can we estimate that? That's tricky. That is tricky. But we can have a look at some of these useful tables in RB209. They give us some figure, and this is from hundreds and hundreds of manure samples over the years, where they've got an idea of some of the sort of characteristics of different types of manure. This table is most useful for this, actually, total nitrogen. It tells you readily available nitrogen as a proportion, as an actual kilogram per ton, but we don't tend to use those actually in our calculations, so don't get confused by those. I'll show you in a second actually how we estimate available nitrogen from organic manures. We use the total nitrogen, then we use another table. But it's just showing you that about 10% is available for farmyard manure, a little bit higher for some of these others. So you use that for total N content of manure. And then what you do is you estimate N supply from manure to the next crop using this table. And I'm showing you the ones for the farmyard manures. There's other ones in RB209 for other types of manure like poultry manure, pig slurry, etc. You can see here that it depends on quite a few different variables. So when you've applied the manure, so for instance, if it's applied in the autumn compared to the spring, there's a slight difference. Now this isn't such a good example because there's not a lot of differences in these numbers depending on when it was applied or the soil type. Other cases there's bigger differences. But in any case, you can see autumn on a sandy, shallow soil, old or fresh manure, about 5% of the total nitrogen in that manure is available to the next crop. That's not very much, is it? If you wait and apply in the spring, then regardless of the soil type, about 10% is available. So why do you think that is? Can you think of that? Any reasons why? It's probably to do with that rainfall and leaching. If you put it on the autumn on a sandy, shallow soil, a lot of the mineral nitrogen in it is going to get leached away before the following spring when you're planting your crop. If you wait till the spring to put it on, then that's not going to happen. So you get about twice as much out of it. So that's why this one in particular is a lot of loss. Let's say losses from leaching. That's what that's showing really, which you're not getting with some of these. In fact, if you apply fresh farmyard manure and you incorporate it, that's the other variable I forgot to point out. You can see here, if you incorporate fresh farmyard manure in the spring, then you can get as much as 15% of the total available to the next crop, because you've minimized loss by volatilization, right? So let me just write that here. Minimizes volatilization loss. That's what's happened there. So there's a bit to take apart in this table if you look at it more closely. There's a rationale for why these numbers are the way they are if you think it through, and think about the nitrogen cycle really, and where those losses are, and what environmental factors cause those losses. Here's a word of caution: don't try to meet the total nitrogen requirement using a manure with a low N availability. Just for fun, if you do this calculation, if you try to supply 170 kilograms of nitrogen per hectare from old farmyard manure, in a way that's 10% of it is available to the next crop, then you'd actually have to be putting on, and what I've done there is, so 10%, so the total nitrogen content of old farmyard manure was 6 kilograms per ton, so 10% of that is available, is that 0.6 kilogram per ton. 170 kilograms nitrogen per hectare times 1 over 0.6 gives you 283 tons of farmyard manure per hectare. That's a lot to spread, you can see. And just remember, when I do this calculation, these have cancelled out, right? And that's how we ended up with tons per hectare. So the total N you would have supplied then, if you did that, would have been 1,698 kilograms N per hectare. Yikes, that's a lot, isn't it? When you think about in NVZs, you're not allowed to put on more than 250 max on any one area, or 170 on average across a farm. So that's really too much, and would certainly raise some alarm bells among the Environment Agency. So you just can't really meet all your crops' immediate nitrogen needs from an old farmyard manure. Even fresh ones, it's challenging to do. Yeah, MVZ rules. You must not spread organic manures on any field at a rate which would result in total nitrogen exceeding 250 kg per hectare. So that you would certainly not be advised to do that. Farm Crop app. Oh yeah, that's an app, and again, that link won't be live in this presentation I'm doing right now, but you can take a look at that. I think it probably still is on there. We might look at it in our practical class actually, and that's kind of a handy little app, again, for figuring out how much nitrogen would be coming from an application of organic manure. So that's a handy one. I think we'll maybe have a look at that on Friday in the practical. And here's another example accounting for N in manure. So this is from RB 209. If your sugar beet is grown on a medium soil after winter wheat, 30 cubic meters per hectare of pig slurry applied in February, incorporated into the soil within 6 hours. And they even talk about average annual rainfall 650, and usually dry winter. Excess winter rainfall was 100 millimeters